To most people, cars are just a way to get from point A to point B, but not a lot of people know how much physics happens behind the scenes when you drive to work.
Every time you start the car, there's a complex series of physical interactions that happen when you hit the accelerator, slam the brakes, or turn the wheel.
Today, we'll cover 7 major physics concepts that happen every time you drive to work, plus one little bonus that you won't see in AP Physics 1. It all begins when you start the engine. In a gas-powered car, the moment you turn the key, the gas in your gas tank gets pushed into the engine, where it combusts, pushing the piston down and the crankshaft. This whole process does one simple thing. It turns chemical energy into a different type of energy, rotational kinetic energy. This is the first major physics concept, energy transformation. Thinking about energy, we know that energy cannot be created or destroyed, only transformed. Car engines are not fully efficient, and only about 20 to 30% of the chemical energy actually gets converted into kinetic energy that moves the car forward. The rest is lost to heat and sound. This is where you get your miles per gallon number. This is all well and good, but you can't just bolt the wheels directly to the crankshaft, because our next physics thing is called torque. In layman's terms, torque is how strong your engine is. Your engine does not produce enough torque to spin the wheels, but it spins very, very fast. This brings us to the transmission. All the transmission does is change the gear ratio from the engine to the wheels. Basically, it says how many rotations the engine has to spin in order for the wheels to spin one rotation. By changing the gear ratio, it multiplies the torque while sacrificing the rotational speed. Think of a sprinter versus a powerlifter. The sprinter, your engine, runs very fast but cannot lift very heavy weight. The transmission turns your sprinter into a powerlifter. The powerlifter can't run very fast, but it can lift very heavy weight. This process exerts a massive torque on the wheels, which lets your car move. Once the torque is applied, the wheels accelerate angularly. Angular acceleration. Just like energy transformation, torque and angular acceleration work reverse and when braking. When you step on the brake pedal, brake calipers clamp down, creating negative torque that forces a rapid negative angular acceleration, bringing the wheels to a stop.
When a car is driving on a flat road, it has forces on it. Gravity pulling the car down, and the normal force, which is the ground pushing back up with an equal force. But vertical forces are only part of the picture. To actually move the car along the road, we need friction. Without friction, the torque wouldn't matter because the wheels would just spin in place. Tires are engineered to have a high coefficient of friction against the asphalt. As the torque is applied to the tires, they push back against the road. Because of Newton's third law, the road pushes forward on the tire with an equal force. As long as the engine's force doesn't exceed the limit of friction, the tires grip the road perfectly without slipping. An instant when the engine's force could exceed the friction is during a burnout, when the tires lose grip on the road, leading the tires to spin in place. But all that won't matter if your wheels aren't touching the ground. This is the job of suspension, to deal with bumps, potholes, dips, and to keep the wheels on the ground at all times. If a car had no suspension, every bump would send shock waves through the car, which is not very comfortable. So to absorb the imperfections of the road, the suspension has to move the wheels up and down relative to the car. The suspension works all around the springs, using Hooke's law, where the force applied to the spring is equal to the spring constant times the displacement of the spring. When you hit a bump or pothole, the force on the spring increases or decreases, and because the spring constant does not change, the displacement must, therefore, move the wheel up or down. When the spring compresses, it stores elastic potential energy and exerts a force to push the wheel back down to maintain contact with the road. Lastly, we have momentum. Momentum is the car's mass times its velocity. Because cars are very heavy objects that travel at high velocities, they have an immense amount of momentum. If you double the mass of a vehicle, like a compact sedan versus a heavy SUV or a loaded truck, that means its momentum is double, regardless of the speed it's going at. Because cars have so much momentum, stopping one requires much greater impulse. This is why cars require large brakes to handle the intense energy transformation as well as a more powerful engine.
When you really think about it, it's crazy how complex a car is and how all these systems work together. A car isn't just a random group of parts. It's a perfectly built system of physics. The chemical energy from your gas tank gets transformed into mechanical kinetic energy and then generates the torque needed for the angular acceleration of your tires. And that rotation would be useless without the force of friction to keep the tires from sliding. And to make sure that friction is actually, there, the springs in your suspension are constantly moving to keep your tires on the ground.
All of this works together so we can safely control thousands of pounds of linear momentum every time we need to go somewhere. Next time you get behind the wheel, take a moment to appreciate the amazing physics transporting you.